Just think for a second about what your phone is doing right now. It's probably streaming this, maybe downloading an app update in the background, getting notifications. But just a couple of decades ago, getting a clear voice call was like the peak of mobile technology. So how on earth did we get from there to here? Well, let's break down that incredible quest for speed. So the big question is, how did this happen? How did we go from just talking to streaming 4K video from basically anywhere? The answer isn't just one single invention. Nope, it's a whole story of clever engineering, some truly revolutionary ideas, and just this relentless push to make our mobile networks faster, smarter, and way more efficient. All right, so our story really starts back in the era of 2G. You might know it as GSM. Now, this was the first digital standard that really brought mobile phones to the masses. But here's the thing. It was designed with one and pretty much only one purpose in mind, and that was voice calls. Data, that was a total afterthought. See, the core technology of 2G was something called circuit switching. When you made a call, the network literally reserved a fixed, dedicated line just for you from the moment you connected to the moment you hung up. It really was like having your own private highway lane that nobody else could use. Which is perfect for a continuous chat, right? But it's completely, wildly inefficient for the kind of stop-and-go, bursty nature of internet data. And because of that, you simply cannot run modern internet traffic on a system that's designed for predictable, continuous phone calls. It just doesn't work. It created this massive bottleneck where trying to send even a simple picture message was this painfully slow process. A fundamental change was desperately needed. And that change came, funnily enough, in the form of a brilliant hack, a clever add-on to the existing 2G system. It was called GPRS, which stands for General Packet Radio Service. And honestly, this was the first real step towards the mobile internet that we all use today. Okay, so this diagram really shows the core difference here. The old way, the GSM method, on the right, it used a fixed, single-purpose channel just for voice. But GPRS, over on the left, it introduced these dynamic, shareable channels that were built specifically for data. This wasn't just a simple upgrade, it was a completely new way of thinking about how to use the airwaves. So what GPRS did was introduce the world to packet switching, which is the foundation of the entire internet. Instead of that private road, packet switching breaks your data, your email, your web page, into these tiny little packets. Think of them like postcards, okay? Each one has an address, they all travel through the network on their own, finding the best route, and then they're just put back together in the right order on the other side. Genius! So how exactly did GPRS get that speed boost? Well, it was kind of a two-part trick. First, it let a single phone use multiple time slots, or, highway lanes at the same time. And second, it used that super efficient packet switching method we just talked about. The result? A network that was finally waking up to the real potential of mobile data. And right after that came Edge, which was even faster. Its big secret was something called smarter modulation. Just think of modulation as how complex the language is that we're speaking over the radio waves. Edge used a much more advanced dialect, called 8PSK, to basically pack way more information into the exact same signal. It was all about squeezing every last drop of speed out of that old 2G infrastructure. But look, all these things were really just clever patches on an old system. The real revolution, the big one, began with 3G, or UMTS. This was the first generation of mobile networks that was designed from the ground up with data being the top priority. And the 3G era saw this incredibly rapid evolution. It started with a baseline called WCDMA, but then it quickly got better with HSPA and then HSP+. You can see each step brought more complex ways of sending data and lower delays. But the biggest game changer that was introduced during this time was a technology called MIMO. So yeah, two key innovations really drove this explosion in 3G speed. First, going back to our language analogy, they upgraded to an even more complex dialect of modulation, packing the data in even more densely. And second, the true game changer, MIMO. MIMO, it stands for multiple input, multiple output. And it sounds complicated, but the idea is actually brilliantly simple. By putting multiple antennas on both the cell tower and on your phone, the network can send and receive multiple streams of data all at once on the very same frequency. It is literally like having multiple mouths and multiple ears to hold several conversations at the same time. And all of this totally set the stage for the network that most of us are still using today, 4G or LTE.
If 3G was about building a proper road for data, 4G was all about building a multi-lane, low-latency superhighway.
Now, a huge part of 4G's success was just simplifying the network itself. In 3G, you had all these separate parts for radio control and other functions. 4G's flat architecture just combined all those functions into a single, much smarter base station called an eNode B. And what did that do? It made the network faster, way more responsive, and it slashed latency. At the heart of 4G is its core network. It's best to think of it like a team of specialists, right? You've got the MME, which is the brain that manages your connection. Then there's the SGW, which is the router directing all your local data traffic. The PGW is the gateway that connects you to the wider internet. And finally, the HSS is the database that knows who you are and what you're subscribed to. This whole team works together to create this blazing fast, efficient, all-IP network core.
Okay, so we've seen all the big generational leaps, but what's really happening under the hood of 4G that makes it so fast? Well, there are two more key concepts that are absolutely crucial to its performance.
So this is actually really interesting. 4G uses different methods for downloads and uploads. For downloads to your phone, it uses a system called OFDMA, which is fantastic at serving tons of users at once from the tower. But for uploads from your phone, it uses something different, SC-FDMA. And this was a very deliberate choice because it's way more power efficient, which is absolutely critical for saving your phone's battery life. And finally, how does the network even handle uploads and downloads at the exact same time? Well, it uses one of two main methods. FDD gives uploads and downloads their own separate frequency lanes like a divided highway. TDD is a bit more clever. It uses a single lane and just switches between upload and download incredibly fast. Both are used all over the world and they each have their own pros and cons when it comes to performance and complexity. So when you really boil it all down, this is the whole story. The entire journey was a move away from those dedicated private roads, circuit switching, built just for voice calls, to an incredibly flexible all-IP packet switch superhighway built from the ground up for data. That fundamental shift, that changed absolutely everything. I mean, think about it. The leap to 4G enabled the entire app economy, video streaming, the connected world we now take for granted. It completely reshapes society. So as we're standing here on the edge of the next generation, the real question has to be, what currently unimaginable things will the next great leap in speed and connectivity make possible?